Okay, I will start. Thanks again. I'm going to talk today about sort of an example calculation due to, the theorem itself goes back to work of Linden, Strauss, and Madsen, and also of Bachstedt. But I'm going to sort of describe an approach to computing the THH of DVRs and their quotients from Achim Krause and Thomas Nikolaus. And this will be somehow a technically much easier talk than all of the other ones so far, but I hope it'll be useful. And it illustrates, in some sense, like a little bit of the philosophy behind this approach to computing K-theory of these finite rings Z mod P to the n that we've been working on. So let's consider some motivating examples. And I'm gonna, I want to study the Hochschild homology of Z over itself. And I'm going to do this in a inefficient way because it'll serve to illustrate a little bit about what's going to happen later. So first of all, what is this Hochschild homology? Well, this has some universal property. It should be the initial, Z algebra with an S1 action, blah, 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 but it's clearly just Z itself. That would be true for Hochschild homology of any ring over itself, any commutative ring over itself. But now I want to compute this using a sort of form of the Gauss-Manin connection. And let me explain what that means in this context. So, of course, the Hochschild homology of Z is a Z algebra, but it's also a Z adjoint X algebra. So I can look at Z maps to Z adjoint X, and then I can map this back down to Z by sending X to 0. And it turns out that there's a fiber sequence relating the Hochschild homology of Z relative to itself and the Hochschild homology of Z over Z adjoint X. So how does this look? Well, so let's do the Hochschild homology of Z of X over Z. So this fits into a fiber sequence. The degree 0 homology is Z adjoint X, and the degree 1 homology is Z adjoint X, sort of dx and then shifted by 1. Sorry, it got a little crowded here. So there's a fiber sequence like this. This is exactly the HKR filtration, if you like. Okay, this is HKR. In degree 0, we have the ring. In degree 1, we have differential forms, which in this case is a free module on dx. Okay, so that's how I'm writing it. Okay. Yeah, I mean, well, it's just in a different category. Sorry, the question is, if I'm sending X to 0, how is this different from just viewing Z as a Z algebra? I mean, it's not particularly different, but their Hochschild homologies will be very different, as we'll see. Okay, so how is the definition of Hochschild homology Z now relative to Z adjoint X along this algebra map? Well, this also has a universal property, but Hochschild homology satisfies some kind of various base change properties. So this is the Hochschild homology of Z over Z, tensored the Hochschild homology of Z X over Z with ZX. Okay, so the functoriality of Hochschild homology means this is a module over this. And this relative Hochschild homology ends up being this tensor product. And so what I can do is I can tensor the Hochschild homology of Z with itself with this fiber sequence. And I get a fiber sequence that looks like this. Hochschild homology of Z over ZX, Hochschild homology of Z over Z, and is this how I'm doing it? Okay, maybe tensoring with this fiber sequence. So this is the middle term, this is the right term, and here I have Huxell homology of Z over Zx, but now there's sort of, I'm just gonna write a sort of symbolic term dx, and then a shift by 1. Okay, that's just what I get by tensoring this sequence with this. And I think it's helpful to kind of rotate this triangle once, and then I get Huxell homology of Z over Z adjoin X. And I'm gonna kind of just write this formal term dx, and then shift it by 2. And I'm gonna call this nabla, because it's really gonna look like a connection. And let me try to prove that for you now. So so these are abstractly equivalent spectra, or but okay, so that'll come up in a bit. So what is this? So I claim that the Huxell homology of Z over Z adjoin X. So this as a ring is isomorphic to a divided power algebra on an element Y. So divided power algebra on an element Y. So this is sort of the subalgebra of Q adjoin Y, containing containing all terms of the form y to the I over I factorial. And how do you see this? Well, you see this by computing the cotangent complex. What is the cotangent complex of Z over Z adjoin X? Okay. Well, the easiest way to see this is, so I've got this map of rings, and that means that there's a fiber sequence. So I have the cotangent complex of Z over Z, the cotangent complex of Z over Zx, and here I have the cotangent complex of Zx over Z, base changed over Zx to Z. Of course, this cotangent complex is 0. It's obviously a tall over Z. And this cotangent complex, well, this is precisely differential forms. So this is a free module of rank 1 over Zx. And now I'm base changing it down to Z. So this is equivalent to sort of a free module of rank 1 on a symbol dx. And then we see that this is Z shifted by 1, okay? Because it's the cofiber of this map. And okay, so now by HKR, so right, I have this HKR filtration. And the ith graded piece is equivalent to wedge I of the cotangent complex of Z over Zx sitting in degree I. That's wedge I of Z shifted by 1 sitting in degree I. And by something else called décalage, this is the divided power algebra, or the ith divided power of Z. You want me to put a dx here? I debated. Thank you. So this derived exterior power of Z shifted by 1 is the same as the ith shift of the ith divided power of Z. And then I've still got another I here. So this is this. Okay, and it turns out that this is multiplicative, and sorry, I should have said that y here has degree 2. X is degree 0. Sorry, maybe I should have, yeah, X has degree 0. This is just an ordinary commutative ring. Okay, and yeah, it's tempting to call y x, but I found that confusing. So now what happens here? So in this sequence, if you think about what's going to come out of this Nabla map, so we're going to get so Huxell homology star of z over z, and then I have this divided power algebra on zy, and then there's some Nabla, and then I have sort of zy again, but sort of shifted by 2. I'm not quite sure what category this is taking place in. And this Nabla is some sort of derivation, and what form must it take to get the corresponding answer? We know this is z in degree 0, okay? And so what has to happen here is that this Nabla of a divided power yi, maybe I'll introduce that notation here. Well, I mean, this is just a statement about the homology groups, and yeah, but I mean, there's no extensions whatsoever. There's a unique contribution in any given, in degree 2i, there's just a single contribution from ger I. Is that, just for degree reasons, right? This is, I mean, this is concentrated in this has homology only in degree 2i. So there's no, the spectral sequence associated with this filtration degenerates, and there's no extensions. That's one way to see what's happening. Sorry, the question was, you know, this seems to be a statement just about the associated graded. So what happens here is that this is y to the I minus 1, and then sort of this symbol dx. Okay. I'll justify this in a moment. Okay. And so this looks much like the Gauss-Manin connection. On de Rham cohomology for this composition of morphisms of commutative rings. Okay, so this is sort of example A, and now let me well, okay. I mean, it looks like it looks like this. In this case, but you know, if you have in general, if you have k to r to s, then the Gauss-Manin connection looks like some sort of like de Rham s over r mapping to de Rham s over r tensored over r with the cotangent complex of r over k, and so forth. And to really make this precise, maybe you want a Kaj complete everywhere or something like that. And in this case, if these ring maps are z to z adjoin x to z, then the de Rham cohomology of z over z adjoin x is a divided power algebra. And here this complex would stop here because there are no higher differential forms in this case that we're looking at a polynomial ring in one variable. Okay, so in this case, this complex would just stop here. We'd have a single sort of connecting map here. So this is you know, more or less this exact same map, but it's sort of spread out in into a different location because of the location of the differential forms here, they're sort of sheared up by some factor. Yes. Well, maybe. Maybe, I don't know. Is this also the homology of CP infinity here? I'm not quite sure. Maybe that it possibly would make sense. I'm not quite sure. Let me give a slightly more general version of this example, where we can see this a little bit better. So let's, instead of trying to compute the Hochschild homology of Z, let's try to compute the Hochschild homology of Z adjoin X mod X to the n over Z. And yeah, it's an isomorphism except for the identity term. Y0 goes to 0, and that picks up exactly that there's a single copy of Z in degree 0. Y to the 0 is the generator of that. Yeah. Thanks. So let's try to redo this computation, but in this slightly less trivial case, and maybe that'll even be less confusing. Now this will be non-trivial, right? This is a more interesting ring, but we can still make the exact same fiber sequence. So this goes Hochschild homology of Zx mod X to the n relative to Z adjoin X, and then the Hochschild homology of Zx mod X to the n over Z adjoin X, and then with this sort of dx term, and then a shift by 2. And once again, how does this look on, oh, maybe I should, right. Maybe it's useful to write this down kind of as a spectral sequence. So one way you can think about this is that there's a filtration, a two-step filtration on this. And the one graded piece is this, and the other graded piece is this, up to a shift, right? You can just think of a fiber sequence as a filtration. And so there's an associated spectral sequence, and then this nabla is exactly the E2 page, well, it's the first differential in that spectral sequence. So we'll write that out in this case, and let's figure out what happens here. Now again, here we could sort of compute this by hand if we particularly wanted to, using the HKR filtration, and you could compute everything that you wanted about this. Okay, but we're going to do it using this sort of connection perspective. And so again, Hochschild homology here. So okay. So this is what? Well, it's related to what Akim was saying in his lecture this morning. By taking this quotient, we're actually getting a bigger ring. Okay, so we're adjoining divided powers to this element x to the n. Okay, so right. This is Z adjoin x mod x to the n, and then adjoin a divided power variable y. And it's exactly the exact same computation. The cotangent complex is once again just going to be a single shift of this ring R. Okay. wait, why am I saying that? Sorry, I'm somehow very confused all of a sudden. Oh yeah, I'm doing it relative to the polynomial ring. Sorry, yep, I was just thinking about this. Okay, thank you. Yes, good. And so again, we get this divided power element here, and then we get the same thing here. So let's look at how the spectral sequence for this looks. Let me call this, for simplicity, R. And then I'm going to get R dot y, R dot y2, R dot y cubed, the divided power, and so forth. And then here it's natural to write this as sort of R dx, R y dx, and so forth. And this nabla is the differential on this page. Okay. And so now we have to figure out what does this map actually do? Okay. So what is this? We sort of have one thing to figure out, which is what this nabla does on y. Okay. So what do we kind of know the answer must be? Well, again, by Hochschild homology, we know that in low degrees, the absolute Hochschild homology is going to be controlled by the absolute cotangent complex. And so we'd better be getting out the absolute cotangent complex, or its homology, in low degrees. And what is the absolute cotangent complex of this map? So once again, you use this composition, and you see that that the cotangent complex. Okay, again, this is R over Z. This is what you're interested in. This maps to the cotangent complex of R over ZX. With fiber, the cotangent complex of ZX over Z tensored up to R. And so this is sort of a free module of rank 1 on an element dx, and this is a free module of rank 1. Well, really, it's I mod I squared, where I is the ideal x to the n, shifted by 1. So we can rotate this back this way and see that this is sort of I mod I squared mapping to here. But of course, this is a quotient by a regular element. So this is also a free module of rank 1 R on a sort of formal class that looks like x to the n. And this map, one checks that this map is the R module map, which just takes the derivative of x to the n here. So yeah, n. So it sends 1. Let me say it this way: 1 to nx to the n minus 1 dx. Okay. That's the. We're basically taking this connecting map is take the derivative of the elements in I. Okay. And so that tells us that this nabla class, nabla of y, is going to be equal to sort of nx to the n minus 1 dx on that term. Okay. Sorry, I guess what I'm saying is, I guess what I'm really claiming is I can choose a basis, I can choose a generator of this. So like up to units, I can choose an element of this where it has this form. And the reason is that, so for example, by the HKR filtration, it's again going to split, or not split, but I mean, okay. So say. So this is going to be a contribution to HH2, Zx mod x to the n over Z. That's what the co-kernel of this map is going to be this. But this is also going to be isomorphic to H. Okay, let me say it a different way. Let's say that the truncation between 1 and 2 of Hochschild homology Zx mod x to the n over Z is actually just going to be the cotangent complex of R over Z shifted by 1. So somehow this just must be quasi-isomorphic as a complex to the cotangent complex. And so sort of up to choosing generators, you see that by comparing to this computation of the cotangent complex that it has to have this form. Okay, so that's this one. And now there's a kind of implicit claim here that the rest of these classes are determined, the differentials are determined by what happens on the generator Y. So why is that? Let me convince you that that's actually the case. Okay, I've got a little board space. Well, here we're going to use the fact that we're torsion free. Okay, so we can kind of multiply and then divide out by things. And so, so I want to figure out what is nabla of y to the I. Well, instead I can multiply by I factorial, and this is nabla of I factorial yi, which is nabla y to the I, and now we can use the Leibniz rule, and this is y to the I minus 1, or sorry, y to the I minus 1, nabla y, and so this is, and now what is, right. Right, okay. So now we're in characteristic 0, well, we're torsion free, so I can divide by I factorial, and then this equation becomes nabla yi is yi minus 1 divided power nabla y. Okay, because when I divide out by I factorial, the i's cancel, and I have a remaining I minus 1 factorial dividing this, which is exactly this. Okay, so that since we're torsion free, this is sort of a legitimate computation, and it determines this entire spectral sequence, and by it determines all of the Hochschild homology groups of this ring. Not, I mean, it might be a little tricky because this ring is torsion, so you have to work out what happens, but okay. So maybe just to conclude here, what I'm saying is nabla yi here. Well, this is yi minus 1 times nx to the n minus 1 dx. And this is some specific element in our ring, right? Okay, and so from here you can work out what is this group, right? I mean, so in particular, so in particular, this implies that. So how should it be? H2 I minus 1 of z adjoin x mod x to the n over z is some specific number, and what is it? It's this ring R mod, let's see, I x to the I minus 1, for example. Are you sure? Oh yeah, sorry, n. N. Right. Yeah, sorry. This n is like the power of x that we're dividing out by. Thanks. Okay, so this is a sort of a toy example of Yes. So this is a toy example of a calculation that we're now going to do in topological Hochschild homology, okay, and will look a little different, okay, but we're going to actually use this example in our computation there. So any questions? We're about to leave this Hochschild world and talk about THH. Repeat this. Well, I guess I'm saying we have this differential, and we know it sends a generator to a specific multiple of a generator. And so then the only thing that contributes to these odd degree classes are the co-kernels there. And so that's just what it is. There's also kernels. There's also even classes here, I think. Yeah. Also, there's, I mean, this is not necessarily 0. Okay. So I just wanted to explain this. This is sort of a easy classical Hochschild homology calculation. And we can use these exact same methods to compute the topological Hochschild homology. And I could have done this, okay, well, yeah, there's lots of other examples to do. Okay. So, okay, any other questions? Okay. So, okay, moving on. So relative THH, and again, okay, well, I was going to say something about the cyclotomic structure, but maybe I'll leave this for another moment, or maybe even just maybe I have switched the board. Yes. Maybe. Right, do I really want to say this? Okay, so let's just be very brief. In general, if I have a map of commutative of E infinity rings, then I can define THH R over K via the same universal property in E infinity rings with S1 action, and I can also define it as THH R tensor over THH K with K along the natural map from THH K to K. Typically, this is not cyclotomic. Remember, a cyclotomic spectrum, X is S1 a spectrum with S1 action and an S1 equivariant map from X to the Tate construction. And the problem with this is, roughly speaking, that in order to preserve a cyclotomic structure on here, you would need to look at the cyclotomic Frobenius on THH of K, and then you would have to find some way of factoring like this. Okay, and so this map was extra structure, and making it S1 equivariant would be extra structure. So this commutative diagram like this does not exist in general. For example, it provably does not exist for K equals Z. And so Hochschild homology is not typically a cyclotomic spectrum. Okay. But there's an important special case where this is okay, and that's the case of K. I'm just going to do the specific case of the flat polynomial ring over the sphere spectrum. So this is, if you like, this is the monoid ring of the natural numbers, but it has the property that its homotopy ring is really a classical polynomial ring over the stable homotopy groups. Okay, so if you have such a factorization, then these are in the literature called cyclotomic bases. Okay, And this is such a cyclotomic base. And the reason that it is, just very, very briefly, is we can make the following factorization. And this was observed first by Bott-Moreau and Schulze, as far as I know. And now, and it turns out that that I can factor this map as the pth power map here, and then the triv map here. The triv map is the one which makes this a spectrum with trivial S1 action, and then maps into the homotopy CP fixed points, and then the natural map to the Tate construction. And so you can prove that this factorization exists by unwinding the definitions of the cyclotomic Frobenius here and using the p power map on the actual monoid n here. Okay, so that's how they do that. So working over THH S adjoins Z turns out to still have good cyclotomic properties, and that's something that we're going to use crucially in the computation of the K-theory of Z mod P to the N that Occam will describe. And it's also used in this Liu-Wang approach to TC of number fields with FP coefficients. They crucially are also using the cyclotomic structure here. Is the action where? On S, here, yes, the S1 action is non-trivial. Yeah. I mean, like this is like S1 CP equivariant. I mean, even if you start with the trivial action here and take Tate CP, it will, in general, be non-trivial, I guess, so. The residual action is non-trivial. Mm-hmm. The vertical maps are not equivalences. No, so that's gonna be crucial. So let me write that down. Just as we had, let's see, how is it? This fiber sequence here, splitting Hochschild homology of a polynomial ring in one variable up like this. Here, we also have a fiber sequence. So this is really THH of S adjoins Z over the sphere spectrum. And this has a canonical collapse map to S adjoins Z. And there's a fiber which is equivalent as a spectrum to S adjoins Z. I'll just sort of write this formal term DZ. Or I can view this as a sort of cofiber here. Okay, and there's a fiber sequence here. Now, it's important to note that this identification is only as spectra. So that I can write this fiber term here in this way, it's only as spectra. And this is sort of, so it's not an S1 equivariant identification of the fiber. That's not going to particularly matter to us for the rest of today's talk, but I just want to mention it. As Z neither are Z modules. As SZ modules, yes. Sorry. I mean, sorry, no. I'm not even sure. Yeah, I guess it should be okay as S adjoins Z modules. Sorry. I mean, but you have to pick a point and use the non-S1 equivariant map to even make THH of S adjoins Z into an S adjoins Z module. And from, yeah, right. Okay, any other questions while I'm erasing? So now what we're going to do is we're going to do the relative version of the calculation, the THH version of the relative calculation from the middle of these boards. Okay. So, and then we're going to use this fiber sequence to get a spectral sequence, a very easy spectral sequence like this, from which one can read off the homotopy groups of absolute THH. And so what we're interested in is sort of complete p-adic DVRs, OK. So yeah, so K a p-adic field, K the residue field. This is the p-complete DVR. I'll write pi a uniformizer. And whenever you have this sort of setup, yeah, and here this is perfect. It's a finite field, in fact. In the cases that I'm interested in, although maybe this isn't completely necessary for the theorems that I'm going to state. Anyways, so this OK can be presented as, well, you take the vid vectors of little k, so this is an unramified extension of ZP, and you can adjoin a variable z, and you can mod out by an Eisenstein polynomial. Where this Eisenstein polynomial is a unit multiple of some power of z, where E here is the ramification index, plus a bunch of other coefficients where P divides AI for I equals 1 up to E, and P squared does not divide AE, I think, in this. Okay, so this is just an Eisenstein polynomial. And the uniformizer pi satisfies some such polynomial, the minimal polynomial of that element in the field. So this is actually an example of a prism, by the way, at least if we complete. Here, this has a Frobenius, a delta ring structure given by specifying that delta of z is 0 or phi of z is z to the p. Okay, so this is a delta ring, and then I use the vid vector Frobenius. And then this turns out to be a distinguished element. Okay, so that's the connection. That's a connection to prismatic cohomology, and these are called Breuil-Kissen prisms. Right. So now we're interested in computing the THH of OK and the THH of OK mod pi to the n. But first, what we're going to do is compute the THH of OK over S adjoin Z and THH of OK mod pi to the n over S adjoin Z. And of course, to make this live over S adjoin Z, I need to tell you where Z goes. And here Z is going to go to the uniformizer pi. Okay, and so that makes these canonically into S adjoin Z algebras, and so we can consider the THH. Now, claim. So first of all, I claim that this homotopy ring of OK adjoin S adjoin over S adjoin Z is actually isomorphic to OK adjoin a polynomial variable in degree 2, as opposed to divided power. Okay, this is an instance of Bachstedt periodicity, and in fact, it's proved. So this is an S adjoin Z module, and what happens if I tensor down THH, let's see, OK over S adjoin Z tensor over S adjoin Z with S, where Z maps to 0. So there's a unique map of E-infinity rings like this. And that, by base change, is THH of OK mod pi, because that's where Z goes to, over the sphere. Or another way of writing that is THH of K. This is a perfect field of characteristic P. So by Bachstedt, this has homotopy a polynomial ring in a degree 2 generator Y. Okay, and so here in here, this Z maps to the class pi in degree 0. And so we're saying this whole ring, mod pi, is this ring. Okay? But this ring is sort of pi-adically complete. So in particular, the fact that this ends up being 0 means that, that all of the terms are pi torsion free. Otherwise, we would get odd classes. And in even degrees, they're just given by single, by free modules of rank 1. And then if you pick a generator of pi 2, then you see that that must generate everything by comparing it to with what happens mod pi. Okay. So this calculation is still in BMS2. I guess it's just yeah, maybe I mean the p-adic completion of this, but that's also the pi-adic completion. I mean, well, okay, yes. Do you need to p complete? Okay, yeah, so let's p complete THH everywhere. Otherwise, no, pi 1 is the units. Yeah. Sounds good. Okay, so okay, and now what's the claim 2? What happens to THH of OK mod pi to the n, let's just call this R for the time being, over S adjoin Z. And here again we see this same sort of pattern. We get a polynomial ring in Y. That's kind of the contribution that's already coming from the fact that this is in particular a THH of OK over S adjoin Z algebra, and then a divided power element in, I'm not sure I have a good name for this, let's just call it X. So here where both Y and X are of degree 2. Okay, so this is the second claim. And the easiest, yeah, right. I just have a long line of equivalences that right. So how do you see something like this? Well, it's going to be by reduction to this previous case that we saw. And you just use that. So let's say R over S adjoin Z. So yeah, you just use this equivalence. Yes, looks good. So this is an equivalent. This is an instance of the equivalence, like THH of sort of A0 over B0 tensor over THH of A1 over B1 with THH of A2 over B2 is is equivalent to THH of A0 tensor over A1 with A2 over B0 tensor over B1 with B2, okay, which is not hard to check. And so here, this particular case is THH of Z adjoins Z over Z adjoins Z. And you see when you base change, you send Z to here, and you take the tensor product with this ring, what is that doing? That's exactly killing pi to the n. So that's putting an R in this variable. I messed something up. Yeah, okay. Yeah. Sorry. Well, this is true, right? This equivalence. Sorry. Oh, did I just? Exactly. Sorry. Yeah. Let me. Actually, yes. Sorry. One more. Here we go. Yes, exactly. Yeah. Yeah, then you use, right, then you use that this map factors through Z, because this is an OK algebra. Okay, and then you can, yes, so then you can prove that. Sorry. Okay. And so, sorry, this map factors through Z adjoin Z, because this is a OK algebra. Yeah. And then you can like make a further tensor product to here, and then remove all of the spheres. Yeah. Thank you. Yeah. Right. And so right. Oh, okay. And maybe it's worth actually writing that out so that we see this. Sorry. Right. So this is then equivalent to THH. Well, I mean with the Z, with the Z's back in, right? And so from which you read off this. Okay. So then you get the tensor. You get a tensor product. Gosh, what a mess. Okay, maybe I just write it out. So this is THH OK over S adjoin Z over, tensor over Z adjoin Z with Z adjoin Z, tensor over S adjoin Z, etc. And then this is Hochschild homology of Z adjoin Z mod Z to the n over Z adjoin Z. And so you see that here we're basically just tensoring the computation that we've already done in this case with the calculation that we just did here, and you end up with this result. Okay. So let me finish up by actually doing the calculation. Maybe I just do it for OK itself, and we see what happens. So, yes? Is that what? Yeah, but I mean, is that true for R? OK mod pi to the n? I don't know. I'm not quite. Oh, I see what you mean. Maybe. I mean, you can write down, I suppose, probably an expression for it and carry it through. Yeah, that seems plausible. Okay, so very briefly, let's kind of now redo a little bit of what we've done here. And we've just computed the relative THH, and what's the feature of this? The point of going to this relative case in both the Hochschild homology calculation and this THH calculation is that we managed to get ourselves into an even situation. Everything's completely algebraic and concentrated in even degrees. And now we can use this fiber sequence here to get a fiber sequence for the THH of OK. Again, everything p-adically complete. And once again, I mean, it's a little bit hard to pin down the exact, S1 equivariance of this object, but that doesn't matter for this specific computation. They have the same homotopy groups, and we know the homotopy ring of this is OK adjoin, what did I call it, Y. And so then you get a spectral sequence, and it looks as follows: OK 0, OK dot y, 0, OK dot y squared. And here you have OK dot like dz, I guess, 0, OK dot y dz. Okay. Now it's sort of much easier because we don't have to worry about the divided powers. We don't have to make an extra argument to figure out how the differential acts on the divided powers. We know that we can compute nabla of the ith power here to be I y to the I minus 1 of nabla of y. And so we just have to figure out what is nabla of y. But for the same reason, this is basically having to compute the cotangent complex of OK, which is often, is that the different in algebraic number theory? So what is this nabla y? Well, it's the derivative of the Eisenstein polynomial evaluated at pi dz in this case. So this is then I y to the I minus 1 times e prime of pi dz. Okay. And now what you see is that the corollary, so this derivative is never 0, right? Because the top term is a unit multiple of some power of z. And so what you see is that that THH 2i minus 1 of OK is isomorphic to OK modulo I times this this derivative of the Eisenstein polynomial evaluated at the uniformizer. And that even groups are 0 because these differentials are all injective, sorry. Okay, and that just sort of falls out of this sort of what I think of as this Gauss-Manin connection here. Okay, yeah? Nabla y, right, so basically this is computing the cotangent complex of OK over z. So maybe I should have mentioned in very low degrees, THH agrees with Hochschild homology. For example, up to degree 2. And so we see that basically this little bit is the same as the little bit in Hochschild homology. And so it must be the cotangent complex. And the cotangent complex, if you unwind how you compute the cotangent complex from like this map, OK, then you find that basically it's given by multiplication by this element. Now, let me just in one word say what happens in the case of OK mod pi to the n, and it's just sort of a combination of the two calculations that we've already done. So R is OK mod pi to the n. And again, we have R, 0, R, and now we have two generators. What did I call them? Well, I guess Y and X, okay. Y and X. And then R, and then what? We have Y squared, the second divided power of X squared, and YX, I guess, and so on. Or sorry, no, I did it wrong, right? Sorry. Y is polynomial, X is divided power, and then we have a term like that. And now I have R dz again, and again, I just have to figure out this first differential. Well, nabla of Y is the same as E prime pi, but now, of course, it's living in this quotient ring R, so this could be, much smaller, and then dz, and then we have to figure out nabla x, and this is going to be given exactly by comparing to the case of Hochschild homology by I guess n pi to the n minus 1 dz. The derivative of x to the n evaluated at pi. And then everything else follows from here by the Leibniz rule. And to really get that correct divided power Leibniz rule, is that the right word? Anyways, you then can compare all the way back to the case of Hochschild homology of z adjoin x mod x to the n over z adjoin x to get how that transforms. And so from here, you can work out, but it's a bit more complicated. Let's say this, in any given case, you could figure out what the homology group is. I think it would be difficult to just write down an exact formula for what the order of the group is, but I think you could do it because these are just maps between some finite, finite rings where you have basis elements for everything. So you could write down a matrix and compute it. Okay, so now, okay, I'm going to talk for 1 minute more. You might hope, this approach to computing THH by sort of descent from this relative version, this is what really motivated a lot of our project to compute the K-theory of Z mod P to the N. And if you somehow had full control over what TP and TC minus of this term would be, then you could potentially also compute the absolute TC minus in TP and use that to compute TC. But this DZ really twists things up, and it's not completely clear how to control what happens when you perform these constructions using the S1 equivariance, because again, this identification is somehow ignoring that structure. So, what Akim will describe in his other lectures amounts to a way around that, but philosophically, it also amounts to a way of computing the relevant part of this. So I'll stop there. Thank you. Oh, do I mean that? I guess it's true, yeah. Each of these lines is actually computing the motivic GER I of absolute THH. That's not completely for free, but that is true. Right, right, exactly. The E2 page of this, the décollage of this would be the motivic spectral sequence, I think. Uh, um, ah. Yeah, I mean, I guess so. Like THH of a number ring is, like if you do the absolute THH, then the terms are finally generated abelian groups in each degree. And so if you like, you can then compute their P completions or their L completions for all primes L. And then you're doing this for the L-adic completions of those. Now, of course, those could split. I mean, you know, there could be several primes over a given L, and then you'd have to worry about how that works. But yeah, no reason why not. Yes? That is a characterization of OK. Sorry, the question is that, and the speaker was pointing, I suppose, to this. And yeah, I mean, the Eisenstein criterion from sort of algebra tells you that the corresponding field extension here is, well, the corresponding, I mean, it's your irreducible polynomial. So you get a field extension, and then this is the ring of integers in that field extension. Similar answers. Well, right, okay. So let's say you do, let me do TP here of OK over S adjoin Z. So I mentioned that this is a prism. And what is this? So TP in degree 2I is, so it's concentrated in even degrees. That follows since this is even and then just degeneration of the Tate spectral sequence. And this is the prismatic cohomology in the sense of Achim's talk of OK over this prism, WK power series Z, and then Frobenius twisted and Roy-Kissin twisted. So yeah, exactly. And then if you did TC minus instead, you'd see the Nygaard filtration on here. Maybe a good, okay, yeah, I'll stop there. Other questions? Right. Yes. Yeah. Right. I mean, yes, I agree. Up to the observation is that we could instead work with like sort of THH of OK adjoin. There's sort of this version of the sphere where pi 0 is the Witt vectors, but it's flat over the sphere, and adjoin Z. And then this is a bit better. Yeah, this would agree p-adically with with just doing it over S adjoin Z. You say we can even take the p-complete sphere? Yeah, for a finite extension, yeah. Yes, exactly, yeah. Yeah, precisely.